right, well, welcome to another demo day. We're excited to have Rick Evans, who's a senior research fellow with the Center for Growth and Opportunity at Utah State University. Rick maintains the OG Core, OG USA, and a few other repositories in the Policy Simulation Library's cataloged projects. And today he's going to talk to us about parametric functions for natural and smooth imputation. Rick, please.
Okay. Got MG is not Max Guinness. Yeah, Jason, you can monitor the chat and folks on. All right, so yeah, thanks so much for having me. Glad the chat's not in the video that's being recorded. This is a presentation, a demo day presentation I've wanted to do for a while. I was kind of looking through a bunch of the things that we've done in our open source repositories, and this topic comes up over and over again. I've titled this presentation "The Secret Sauce of Stitching Functions," but it's really just about how do we take kind of the most parsimonious parametric functions we can in order to impute data and have it be smooth. And oftentimes you want it smooth in both just the levels and the derivatives. So you've got smooth derivatives where you've got stuff imputed, and you want it to match a few different criteria. This is something that we've used all over the place in the macroeconomic repositories, open source repositories of OG Core, OG USA, and then I actually put a fourth example in my list of things for a paper that Kirk Phillips and I wrote about elliptical utility functions. So let me share my Google Colab notebook. I put a link to this in the chat. So it's the first post in the chat. So any of you can follow along with this notebook. As I jump down in the text, this key questions, these are the questions I'm usually trying to answer when we impute a parametric function to kind of fill in data that's either censored or truncated. We know what are the properties of the function that we want to impute. Sometimes those include smoothness, monotonicity, single peakedness, asymptotes become really important. And then we switch to the question of what is the most parsimonious parametric function that delivers these properties. Parsimonious, we want that in terms of what's the fewest parameters that deliver these properties. And then also we spend a lot of time on what's the family of functions that will deliver these properties. Then the final question is, how do we uniquely identify these parameters, or can we uniquely identify these parameters? I'll show you 3 examples where the parameters are uniquely identified, and then one example, actually the first example, where they're not, and for some interesting reasons. So the examples I'm going to go through are, the first one's going to be imputing lifetime earnings after age 80. The data in the US only go up to age 80, but the model has ages from 80 to 100 also. The second example is kind of in the core logic of the overlapping generations macro model, has to do with the marginal utility of consumption. Then the third example has to do with fertility rates in the macro model for the UK. And then I just put a little reference to that elliptical disutility of labor paper. But like, if you look at the functions, we're going to pull out an arctangent function. Like, I've got kids in high school right now that are doing trigonometry, and they ask me, when am I ever going to use this? And I can say I've got arctangent in my work. And so this will be fun. And feel free to stop me and ask questions if you have any as we're going through. So this first thing I want to look at.
Post the link again in the chat to this.
Yeah, let's see. Nope, that's not it. Let me try that again. Yeah, okay. There we go.
Thanks, Rick.
All right, so I posted the link again in the chat. Anyone can follow along. This first example has to do with kind of calibrated earnings profiles for individuals in the USA macroeconomic model, OGUSA. So what you're looking at here is a picture of really the data are log of hourly wage. And Jason actually is the person who really set this up and did this, where he went to the IRS statistics of income. What data is it? It's the continuous work history sample. And that data, those data go from age 20 to age 80. In the OGUSA model, we have ages, it also includes 80 to 100. So that vertical dotted line shows you kind of where the data end, and we needed to impute these paths after that point. And so you might be looking at this, actually, before I go on, the 7 different lines are different lifetime earnings percentiles. So that top line is the top 1% of lifetime earners and what happens to their hourly wage over their life from age 20 to 80. And then the bottom line, dark line, is the bottom quartile, 0 to 25%. What is their hourly wage over their lifetime? So we need something that goes from 80 to 100. And here are the characteristics that we wanted these to have. So I'll jump back and forth between these bullets at the bottom of the screen and the picture at the top of the screen. The imputed log wage functions from 80 to 100 need to connect to the data at age 80. So that's one condition. We want whatever these imputed functions, we want them all to connect there. We'd love to have the slope of the log wage functions equal to the data. This one looks like that hits, that one, the slope looks the same. Looks like that one doesn't, that one certainly doesn't, this one doesn't, and that one doesn't. So some of these are broken. The slope of the imputed log wage functions are negative and declining monotonically. So that's just a condition, kind of a characteristic of the theory. As people get older, their hourly wage and their productivity is just going down. Like their human capital and physical capital are depreciating. So where were we? The last 2 bullets, the imputed log wage functions asymptote to some positive number, probably 0, right? So the idea is that these functions should asymptote to 0 as age goes to infinity or as age goes to 100. You can see that it's not clear that that's being satisfied. And we also want the rank order of the log wage functions at 80 to be preserved in most cases. If we look at this, I don't know, this the top 9%, sorry, the 90 to 99th percentile, we want that to be higher than the next decile, 80 to 89%, but at the very end of their data, they go below the 80 to 89%. So we actually fixed that in the imputed data. But in general, we want the rank ordering at age 80 to be maintained. All right, so what we ended up using an arctangent function. And so a general arctangent function looks like this. We want the negative of that though. So general arctangent function has these properties where the domain goes from negative infinity to positive infinity. The range is between pi over 2, negative pi over 2 and pi over 2. And it has these asymptotes. If we flip that to be negative, here's the function we came up with, where we divide both sides by, or we divide the function by pi, and that changes the range to be from negative 1/2 to positive 1/2. We multiply by negative a, which flips this function and makes the range from negative a over 2 to positive a over 2. Then we add a over 2 to make it go from 0 to a. And then we just added in, instead of just x, we have bx plus c. So what we can do is manipulate kind of the slope of that function and how quickly it transitions and where it crosses the midpoint. And basically we can attach that to satisfy those properties that we wanted to the end of these functions. And so here's some code that does this. So I'm importing NumPy and Matplotlib. I am executing this function, putting this function into memory. This function's taken directly, arc10_func is taken directly from the income.py module in OGUSA, and I've links to those. And now I can create this new arctangent function that has these coefficients for the parameters A, B, and C, and I can plot that for a minimum X values and maximum X values. And it looks like this. You know, if I change the C function, that's going to move this plot backward and forward. So it's going to kind of cross 0 at different points. Let's see if I plot that. We plot that for a different. Let's try -30 to 10. Yeah, you can see it moves the plot side to side. If I change the B parameter, it's going to change the slope of this thing. And then we just have an optimization routine that takes this function and estimates A, B, and C to satisfy those properties that we wanted. And that, with a few exceptions that we coded in, that is how we got these imputed values. And that's all in the open source code, and people can go to that and criticize it or propose improvements. Actually, going through this, preparing this for today's demo day, I saw some things that we could improve in this. I guess the thing I want you to take away here is we list what properties we want the functions to have, and then we write a function that has those properties, and this is a 3-parameter function with A, B, and C, and then we just implement that in our code. We estimate the parameters and stitch these functions to have these properties. Any questions on this lifetime earnings example before I move on? Okay. The next one, this marginal utility of consumptions example, this is one that ended up being a really key speed up in what's a large, a super big nonlinear equation, simultaneous equation, nonlinear root finder problem. So in the OG core logic for the big macroeconomic model that gets used in all of the country calibrations, the households in that model have to choose a consumption decision, a labor supply decision, a savings decision. And those decisions are categorized by these 3 equations. And these are pretty ugly and complicated. But if you look in the paragraph below those equations, for every type of household, there's 7 types of households. They've got to solve 160 of these equations every period. So that's, 1,120 equations every period, and for 300 periods. And so that the equilibrium in this macroeconomic model on the household side is 1/3 of a million equations and 1/3 of a million unknowns. That's a really hard optimization problem to solve. And so one speed up that we put into this is, instead of solving a minimization or a maximization problem, we characterized it as a root finder problem, setting those equations, finding the 0 function for those 3 sets of equations, all 336,000 of them. And then just making sure in the theory that the conditions for a root finder to be uniquely identified are satisfied. And one thing you'll see in this root finder is you'll see a term that looks like this, c to the negative sigma, and that's the marginal utility, the derivative of the utility function. You see that all over the place. You see it there, here, c to the negative sigma. You see it here with a different variable, here. So this marginal utility functional form, c to the negative sigma, is really important here. And if I plot what that function looks like, I'm just going to execute these 2 blocks of code. The marginal utility function is really only defined for strictly positive consumption. And you're basically setting the marginal benefit of consumption equal to the marginal cost. So the right-hand side of those equations that I showed are some increasing function that crosses this, and the root is going to be where those 2 things cross. The problem is, if the root finder guesses a consumption that's too high, the Newton method is going to give its next guess to be lower, and sometimes the next guess might be a consumption that's negative, and that'll show not a number, and it'll break the root finder and it won't solve. So we needed something that allowed this root finder that's much faster to keep going, even if the root finder guesses something out of this range. And so we came up with stitching a function, a linear function, to this marginal utility at some point that's really small but positive, and have it just be linear, but it's defined for consumption that's negative also. And so linear, that's a 2-parameter function, and that implies actually with the utility function, a quadratic utility function that we're stitching on the end of this thing. And there are 2 conditions that we wanted. We wanted it to be attached at some epsilon that's low, but then the 2 conditions are that the value at that epsilon is the same as the value of the original marginal utility function, and that the slope was equal also. So those are those 2 conditions, and you can actually solve for the parameters of the line that fits that way exactly. We don't need any solver to find those. And so this function, marginal marg utility consumption, this is taken directly from the household.py module of OG core. Just going to execute this, and this has the stitching function, and this will show you what that looks like. So you can see the original marginal utility looks like that, and I've noticed the scale's way different here. And that we've stitched this linear function to match the level and slope at some epsilon. I think the epsilon it's hard-coded in this function at 0.003. And all that does, we know that these areas of consumption from 0.003 or lower are not where the solution is going to be. But all that stitch function does is it pushes the root finder back into the feasible range of consumption in a way that's much more computationally efficient than a minimizer or a constrained root finder. And so that's some pretty slick code that's been implemented in the overlapping generations model. That model, by the way, is highly parallelized. So you can, it's parallel processing those 1/3 of a million equations and unknowns. And then just the optimization routines inside of each of those parallelized processes are also sped up, I mean, by an order factor of 10. So this is really important. This makes any OG core models run in 2 hours instead of 20 hours, which is a big deal. All right, so that's that example. Any questions about this example? Okay, then I will just move on to the last example and then open it up for questions at the end. So this one is the code I'm going to show here is part of an upcoming pull request to the OG UK model, the macroeconomic model for the UK, and it involved calibrating the demographics of that model. So in this model, it's really important to have fertility rates by age. So the rate at which people are born at each age, and the ages in the model and the demographics go from age 0 to age 100. So I'm just going to install this Eurostat Python package because we're going to be taking these data from the Eurostat organization and their API. Okay, so that's loaded. Now I can import. I'm going to import the Eurostat package and use pandas, and I'm going to import births by age, download those directly from the Eurostat API. So you're going to see, this is going to, okay, now it's downloaded the births data. So if I plot the births data, this is births by age. That looks pretty good. What you can't see is at the end, there are these categories, year 10 through 14. So at the low end, it just aggregates births for anyone ages 10 to 14. And at the high end, it aggregates births for anyone 50 or greater. And so if I zoom in on those, let's look at the 50 or greater. You can see it goes 47, 48, you've got births on the y-axis, 49, and then 50 or greater that's 263. So it goes up. What we really want to do is take those 263 births for 50 or greater and spread those out continuously to kind of follow this pattern, this downward pattern of fertility rates, right? So this, you can see that downward pattern zoomed out here. And we want it to have the following properties: that at age 49, the parametrized function matches up with the data. And at some maximum age, the number of births for that age is 1. So the lowest number of positive births that you can have. And then the last thing is, for any values that have positive births, we want it to add up across those imputed values to 263. So the function, we're going to use just a 3-parameter exponential, where ax raised to the b power plus c. And I don't have the code here. Let's see, where is this code? I think I'm going to skip sharing my screen on this. I just put the screenshot of the final fertility rates that use this code. But it makes a nice smooth fertility rates transition instead of that the uptick at 50 that were in the data. And it also does the same thing at the low end, but it spreads, I think it's 72 births. Let's see what it actually is. At the low end, yeah, I think that's 72 births at the low end for ages 10 to 14. So this function is going to spread those out evenly using ax plus b, ax raised to the b power plus c, and just gives us some smooth functional forms. I did include one last thing just as a note here, where Kirk Phillips and I have a paper. It's down here in the references, Advantages of an Ellipse when Modeling Leisure Utility, where basically there are these functional forms used commonly in the microeconomic literature. Frisch elasticity, the Frisch elasticity disutility of labor functional form, or the constant relative risk aversion utility of leisure functional form. And those had some issues at the upper and lower bounds of possible labor supply. And we found that the functional form for an ellipse satisfies both of the deficiencies of those two approaches. And so we fit an ellipse to match the those two functional forms as closely as possible, and then use that in our disutility of labor functions. And that's just yet another example. The elliptical disutility of labor was another 3-parameter function that we estimated those parameters to. This was more of a regression type, nonlinear regression type problem, where we fit those 3 parameters to match up with the original utility functions. So I think that's all I want to say. I've got a link to this Google Colab notebook for anyone to use. I'll put that in the blog post for this demo day, but happy to answer any questions.
Rick, that was great. But I see 4 examples, 4 different functional forms. How do you advise folks on, if they want to implement something like this, they know there's a computational problem with a kink or a corner solution that the solver keeps tending towards? How do you think about what functional form to use, whether you need to use an arctangent or a linear function or an ellipse or what have you? Like, what kind of advice can you give folks in that regard?
Well, I don't know if this is going to be satisfying or encouraging, but the answers range from just pure science and theory to art. I mean, if we look back at the example of the lifetime earnings profiles, like, this was literally art, where we wanted to just paint what is my intuition of what these lines should be. And then we kind of looked through the catalog of different functions that we could use, and which ones are the most parsimonious. That one is pure art. The marginal utility of consumption one, where we stitched that linear marginal utility function to the consumption function, I have to give Ken Judd credit for that. Ken Judd is the one who taught me this trick. And like literally that trick gives you a 10 times speed up. So you don't have to do a constrained root finder. You don't have to do a constrained minimizer. And, so part of this is just how clever are you? And you do have to know what different functions look like. Functions that keep coming up for us are like exponential functions, functions that decay monotonically or increase monotonically, and functions that asymptote end up being really important. So matching asymptotes are part of this. And then examples that I didn't give, there's a whole really interesting theory on as you go to higher parameter distribution functions, but they're still parametrized. So you're not doing like a kernel density function, but like I think of the generalized beta family of distributions that can be skewed, the domain is positive. It's really hard to just straight up estimate a 5-parameter generalized beta distribution. And so there's this way, if you start with nested lower dimensional, lower parameter functions, and then use those as starting values to estimate the next function, that's another trick that we've used quite a bit. And that's really a trick of the trade. That's a trick of optimization that reduce the dimensionality of the problem and then slowly ramp that dimensionality up. And that's going to help you solve really highly dimensional nonlinear system of equations problems.
And I do like that, yeah, and this is one of the things I think is exciting about computational economics, and you've illustrated here very nicely where, you've got to know something about the theory or the data here, because that's informing, what is that slope of that utility function, or what do I think the data look like between these bins that we see in the tabulations that are made public or what have you. So it's really nice application here where you can see that you got to have some intuition for the data and also understand your economic theory to be able to implement these solutions and tie in that kind of computational aspect.
Yeah.
Awesome. Well, Rick,
Well, cool.
Thanks so much.
Yeah, thank you guys so much.